Hi everyone, I'm Xinzhe from MIT Lab for Information Decision Systems. Today I'm going to present our paper, Elastic Job Scheduling with Unknown Utility Functions. This is a joint work with my advisor, Professor Eytan Modiano. In this paper, we study the problem of elastic job scheduling with unknown utility functions. At a high level, the problem setting is to decide on the sizes of incoming jobs, route the jobs to servers, and tries to maximize the total utility. However, different from traditional job scheduling or resource allocation problems, here we do not know the utility functions of the jobs, but only receive observations of utility values upon job's completion. This problem can model many real applications, especially where the jobs are malleable in nature. For example, we consider the case of the training machine learning applications, like we are executing a gradient descent algorithm to estimate some model parameters. The size of the job here corresponds to a number of iterations of the gradient descent, and the utility of the job measures the quality of the estimated model. So then the job size is usually tunable, and the utility actually depends on the job size. But typically, the functional relationship between the job size and the utility is unknown a priori, but we can receive observations of utility values after the jobs are completed. Hence, based on the problem we are trying to solve, we propose the following concrete formulation. Consider a discrete time system with k classes of traffic and a time horizon of capital T time slots. At each time, AKT jobs of class K arrives at dispatcher UK, with the dispatcher UK connected to a subset of server SUK. We then decide the job size of class K as xk of t, that is in the bounded set 0 to capital B as an upper bound. And then we route the jobs to the servers. For each server SM, its offer service rate at time t is denoted as TSCMT. And based on this definition, we also define the queue length or the workload server SM at time t to be evolving as this recursion, where the variable m is the total evolving workload to server SM. Further, each class is associated with a utility function that are non-decreasing, concave, and Lipschitz continuous. The utility functions are unknown a priori, but we can receive observations of function values based on the completed jobs. So specifically for a class K job of size xk, we can observe and obtain fk of xk plus a noise when the job is completed. So the noise is assumed to be IID and of zero mean and with bounded support. Finally, the arrival and the offer services are also a sequence of IID bounded random variables. We assume that we can observe and observe the realized arrivals and services, but we do not know their means. So the goal of the problem is to design a policy that decides on the sizes, the designated servers of incoming jobs, so as to maximize the total utility obtained by the end of the time horizon. We will use U pi t to represent the expected utility under pi, and pi star to represent the optimal policy. So in this work, we will use regret as a performance metric, which is defined as the gap between the expected utility obtained under our policy and the optimal. So basically, we want to have a policy whose regret is a sublinear function of the time horizon p. Based on the formulation, I will proceed to present the main results of our work. First, I will give some bounds on expected utility. More specifically, I will first give an upper bound on the expected utility of the optimal policy, and then a lower bound on the expected utility of the any policy, which will lead to a key upper bound on the regret of any policy that is instrumental in the analysis of the policy we will propose. We consider the set lambda defined as follows. Lambda can be interpreted as a stability region of a network. If we take a closer look here, X can be thought of as a set of steady-state job size vectors. Alpha encodes the steady-state routing variables that represents a proportion of jobs that are sent from each dispatch to the servers. Lambda basically represents a set of job size vectors that the system can support in steady state. Note that a set lambda involves unknown parameter lambda and mu. So it's not readily available, but it can be used to establish some auxiliary bounds. We first consider this following optimization problem P. It asks for the job size vector X that maximizes this objective function. P can be thought of as a static version of the decisive job scheduling problem. If we just plug in all the parameters of the job scheduling problem as their means. So our first result shows that the expected utility of the optimal policy is actually upper bounded by t times the optimal value of this optimization problem P. The result is proved by simply applying Jensen's inequality. And next, we show that for any policy, its expected utility is lower bounded by the total utility of the jobs dispatched minus L times the Q length at the end of the time horizon. This follows simply from the assumptions that the utility functions are L Lipschitz. Hence, the expected utility of the incomplete jobs in the queue is upper bounded by L times the Q length. Based on these two bounds, it follows that the regret of a policy can be upper bounded by the sum of these two terms. The first one, which is we call the utility regret, is in a sense the gap caused by the suboptimal job size decisions. The second term we call queuing regret, which is composed of incompleted jobs in the queues. So intuitively speaking, if we can make sk of t close to xk star, then the utility regret will be small, and the queuing regret will also be small since x star is in the stability region. Here x star is the optimal solution to the optimization problem P. So therefore, this bound shows that there's a close connection between solving the elastic job scheduling problem and solve this problem P. Note that for P, we only have zeroth order, or to say banded feedback of the objective function, and the constraint x in lambda is unknown and is parameterized by the means of stochastic processes. Hence, the elastic job scheduling problem has closer connection to convex optimization problem with banded feedback and stochastic constraints. And also based on this link, we can show that actually a lower bound on the regret of the elastic job scheduling problem is at least square root of t. So previous work on convex optimization with banded feedback can be classified into two categories. The first category, for example, works 2 or 3, propose first-order methods which essentially use utility observations to construct a proximate gradient of the utility functions. These methods in general cannot achieve order optimal regret due to the variance of the proximate gradients. And the second category proposes zeroth order methods, which basically directly work with the utility observations. Usually, these methods maintain a target region that contains the optimal solution and directly use utility observations to shrink the target region. Zeroth order methods are usually robust to noise, but cannot handle stochastic constraints like the ones in the elastic job scheduling problem. Our main contribution in this work is extending a state-of-art zeroth order algorithm to handle stochastic constraints and achieve order optimal regret for the elastic job scheduling problem. The algorithm our policy is based on is a stochastic convex banded algorithm proposed in 4. It was designed to solve convex optimization problems of this form with banded feedback, where at each iteration we can query a point and receive a noisy and biased observation of the function value. So if the feasibility region is known, then the SCPA algorithm achieves square root t regret. Here, this tilde has logarithmic factors of t. So that is, it will upload a sequence of query points such that the cumulative difference in terms of function value with respect to the optimal is in square root t, order of square root t in expectation. So to better understand how the original SCPA cannot handle stochastic constraints and how we extend it, here I'll give a brief introduction on how it works. So the SCPA algorithm maintains a target region in which is initialized as a feasibility region. And the target region is a set that with high probability contains the optimal solution. SCPA proceeds in phases. In each phase, it first repeatedly queries a set of points in the target region, and each query corresponds to a decision at one time. So the query points output by SCPA usually contains multiple consecutive points of the same value. And next, the algorithm constructs confidence intervals of the function values of the query points. Since we have unbiased observations of function values, the confidence intervals are simply empirical mean minus or plus some margin. And finally, the algorithm eliminates a fraction of the target region based on the confidence intervals and proceeds to the next phase. So from this description, we can see that the SCPA will not work without knowledge of the feasibility region. So to extend it for the elastic job scheduling problem, we start with the original optimization problem P and create a transformed problem P tilde. In P tilde, delta denotes the L1 distance to the set lambda. So P tilde is basically P by replacing this hard constraint with a penalty term. We can show that P and P tilde are equivalent, that they have the same set of optimal solutions, and also the objective of a function of f of P tilde is also concave and Lipschitz continuous. Hence, if we want to solve P for the elastic job scheduling problem, we can equivalently work with P tilde. Here, P tilde is nice in that it does not involve stochastic constraints and is thus more amenable to SCPA algorithm. However, there is no unbiased observation available for the objective function, this capital F of P tilde, in the setting of elastic job scheduling. So therefore, to use SCPA for P tilde, we need to design a special procedure to construct confidence intervals for capital F using the information available in the elastic job scheduling problem setting. So basically, the question we face is that if we decide on xt to be x for t from t1 to t2, then how to construct a confidence intervals around the value f capital F of x? We will assume for now, for ease of argument, that the utility observation is immediately available after the corresponding job size decision, instead of after the job's completion. That is, there's no feedback delay. We'll remove this assumption afterwards. So then, from the time slots in the interval from t1 to t2, using empirical mean of the utility observations, we can construct a confidence interval of fk of xk for each k. And also, using the empirical mean of the realized arrival and offer services, we can construct confidence interval of the arrival rates of lambda k and service rates mu n. We will show that these confidence intervals can propagate to a confidence interval of capital F of x. So recall that the set lambda of the stability region, it is a set that is parameterized by the arrival rates and service rates. We can show that by plugging in the upper end of the confidence interval of the arrival rates and the lower end of the confidence interval of the service rates, we get an upper estimate of the delta value. And doing the reverse, we will get the lower estimate of the value delta. So therefore, accordingly, we can use this confidence interval of delta together with the confidence interval of utility functions to form the confidence interval of capital F. And we can actually further show that such confidence intervals satisfy the requirement of SCPA. And thus, SCPA embedded with such confidence interval construction procedure can be used to solve tilde P. Therefore, for the policy we design, we have the components that decide on the job sizes. So for the routing part, we simply use the join the shortest queue routing. Basically send the jobs to the servers with the smallest value of QMT. So we call our policy the confidence interval join the shortest queue policy, CIJSQ. So basically it's an integration of the SCPA algorithm embedded with the confidence interval construction procedure we just described together with the JSQ routing. So we prove that the CIJSQ policy actually achieves the optimal square root T regret. So the high level idea of the proof is that from the guarantee of the SCPA, we can have this bound on the cumulative difference between our job size decision and the optimal decision with respect to the objective function of P tilde capital F. And then from this, we can actually first show that the utility regret is of order square root T. And we can also show that the cumulative constraint violation is also of square root T. Then we use the properties of join the shortest queue. It follows that the queuing regret is also in square root T. From we can just do this by a drift argument from a constraint evaluation bound. And finally, to deal with the feedback delay, that is that the utility observations are not immediately available after the job site decision, but is available after the job's completion. So to deal with this feedback delay, we propose an episodic scheme that has the same order of regret. So we will have more details of this episodic scheme in our paper. So to summarize, we consider the problem of elastic job scheduling with unknown utility functions. The problem can be viewed as a problem of convex optimization with bandit feedback and stochastic constraints. And we combine the SCPA algorithm with the confidence interval construction procedure to form a policy with order optimal regret for the elastic job scheduling problem. So based on our knowledge, this is actually the first work that extends the zeroth order methods to problems with stochastic constraints.
So this concludes the presentation. I would like to thank you all for your attention. If you have any further questions, please feel free to email me at my first name at mit.edu. Thank you.